All right, good morning, everyone. So let me try to share my screen. So the plan for today is to first finish off with this time delay. We will discuss how we can use the time delay to make an approximation of higher order systems with systems of lower order, but with a time delay. So we will use this time delay in order to reduce kind of the order of the system. And that is relevant for us because we know we have some design tables that we can use in order to design PID controllers for specific lower order plants. In particular, we have seen first order plus dead time. If it's given as the system model, we can actually use our design tables in order to design a PID controller, at least as a starting point, which will give us a reasonable behavior. Okay, so we will now learn about a technique we can use when a higher order linear system is given. We can introduce a time delay as an approximation in order to obtain a lower order system with time delay. And you can also obtain a first order plus time delay system. And you can then proceed to use some of the design tables in order to come up with the controller. Following that, we will go through how this PID controller formulas are coming about. Okay, so we will cover the derivations of some of these formulas to see how they have been developed. Okay, so let's start our discussion. I believe we are at week 11. Okay, today is the 21st. So let's put a title on this. Okay, so this is approximation of higher order transfer functions, higher order TFs with lower order plus dead time. Okay, you can find this discussion also in Chow's book. Okay, I try to basically give you, if I don't forget, I try to give you the corresponding chapters from our reference books, but almost all discussions that we are having in class are actually covered in one of our reference books. Okay, so if you want to find a different discussion or a different way of presenting the material, you can always go to one of these reference books to basically reread that discussion from there. Okay, that would be very useful. All of these books are you can find them over the internet as PDFs, so you should have no problem there. Okay, so as we can approximate a transfer function with time delay with a higher order rational transfer function, we can also go the other way as well. Okay, remember in the PADE approximation, what we have done is that we use the PADE approximation to add an unstable zero and a stable pole to the system, so the order of the linear system was increased, but we basically got rid of the time delay. So it was a linear approximation to an infinite dimensional kind of transfer function. Okay, so how does that go? So let's say we are given a higher order transfer function. With let's say n poles. So we have n time constants. Okay, so let's call these time constants tau 1 to up to tau n. So we basically assume that we have let's say a gain over tau 1s plus 1 up to tau ns plus 1. And let's also assume let's say tau I and tau j are the let's say dominant or even just the largest time constants. Now, if they are really dominant, okay, we know that we can even not use any time delay in the approximation. If you have a number of dominant time constants, that means they are largest, meaning that the corresponding poles are closest to the j omega axis. Sorry, I'm trying to find my own video somewhere. Okay, let me pin that for your recording. Okay, what I was saying is that if you have, remember the dominant pole condition, if the pole is at least 5 to 10 times farther away from the j omega axis as the remaining poles, if the poles are close to the j omega axis and the rest of the poles, the non-dominant ones, are at least 5 to 10 times farther away from the j omega axis, in fact, you can just use the dominant poles in the linear transfer function. You can just forget about the rest because the slowest behavior will be dominated by these poles. All the rest of the poles will have just a transient at the beginning. Okay. Now, what I'm talking about right now is a better approximation than simply discarding those non-dominant poles. Okay. Therefore, it can even be used when the non-dominant poles are, let's say, 3 times or more kind of farther away from the j omega axis. Okay? Arkadaşlar, ne demek istediğimi anlatabiliyor muyum bilmiyorum ama şöyle ki hani dominant pole kavramını biz şu anda anlattığımız yöntem olmadan da kullanabilirdik. Eğer non-dominant pole'lar yeterince uzaktaysa j omega ekseninden, o zaman direkt onları discard da edebilirdik. Şimdi discard etmeyeceğiz. Onları bir time delay'e toplayacağız özetle. Okay? So let me show you what I mean. So these dominants, these are the ones closest to the j omega axis, and hence determining the dominance rate of decay in the exponential function. Okay, then g of s can be approximated by basically a system with the dominant or largest poles, those that we have just stated, tau I s plus 1 and tau j s plus 1. And in the numerator, you will have the same gain, a time delay, theta ds, and the time delay is calculated as the summation of all the non-dominant poles. Okay, so L, which is different from I and J, tau L. Okay, so that's the approximation. So remember that the non-dominant poles will have faster exponentials, so they will just contribute to some kind of a transient at the beginning of the response. Then the response will converge to first or second order dominant behavior. So what we are saying here is that we can approximate that transient period with a time delay, which is calculated by just summing up all the non-dominant time constants. Okay?
Doğru kullanımı bu değil mi? Yani hani biz eskiden dediniz ya sizde direkt atıyorduk, hiç time delay falan eklemiyorduk.
Well, it really depends because just having something without a time delay is much easier for the rest of the task. Okay, so if the dominant poles are really dominant, meaning that they are, let's say, 10 times the time constants are 10 times larger than the other time constants, you can still do without the introduction of the time delay, because that time delay will be very small. Okay, according to this approximation. Okay, so both has its place, but clearly this is a better approximation, but it introduces more complications because a system with a time delay is more difficult to analyze. Okay, the upside is that there are design formulas derived from the presence of this time delay, so it gives you the ability to directly use those design formulas. But if you want to do, for example, a root locus analysis, introduction of the time delay just makes things more complicated. Okay. Arkadaşlar, birinizin mikrofonu açık. Biraz gürültü geliyor o taraftan. Mikrofonu kapatabilirse sevinirim. Okay. Any other questions? So note, obviously I have shown you this on a second order kind of dominant pole assumption. So we ended up with a second order plus time delay system, but this can obviously this can also be applied simply to find an FOPDT approximation to a higher order plant. Okay, so let me show you an example with that to make things a bit clearer, and then if you have any further questions, we can go over them. Okay, so example. A linear approximation to interconnected free-flowing simple tanks By the way, this is a good physical example. It's an example where one tank has an outflow that is going into another tank, which has an outflow that is going into another tank. So each tank obviously adds to the order of the system. Okay, so the more tanks you have, the higher the order of this system. Okay, is given by G of S 3 over 0.1 S plus 1, 0.5 S plus 1, S plus 1, and 3S plus 1. Okay, so you see that this is a fourth order system, but you can see that there are different time constants. 0.1 is a small time constant, 0.5 is a small time constant, 1 is a not so small time constant, and 3 is the largest time constant. Okay, so we don't have that kind of a major dominant pole here, but there is certainly a largest pole which is 3 times as large. Sorry, the largest time constant, not the pole. The pole is the smallest, right? Which is at least 3 times larger than the next biggest one. So the question is, okay, let me put it here. Our questions, find an FOPDT model for the system, and following that, find a suitable proposal for a PI controller for the system. Okay, so the fact that we need to find a first order plus dead time model for the system actually forces us to pick the largest time constant and not worry too much about how dominant it is. Okay, obviously the more dominant it is, the better the approximation, and the closer the second time constant to the most dominant time constant, you can know that the actual system response will deviate from the approximation. So you will start losing some performance in terms of both the system approximation as well as the designed controller. Okay, so solution is starting with the largest time constant. So the largest time constant is at tau is equal to 3 seconds. Okay, so that means our pole is at, obviously, S is equal to -1/3. So this is the pole which is closest to the j omega axis, obviously. So the approximation goes like this. G tilde of S is 3 e to the minus theta ds. Same gain, we preserve the gain, but we introduce a time delay, and we preserve the largest time constant. Okay, so the initial transients can be approximated by a time delay theta d, which is given by simply that summation of all the rest of the time constants. Okay, I is equal to 1, 2, 3, assuming that this was the fourth time constant, tau I, and that is equal to 0.1 plus 0.5 plus 1. Okay, so our time delay in this case turns out to be 1.6 seconds. Okay, so what is our FOPDT model? right? Our FOBDT model is simply G tilde of S is equal to 3e to the minus 1.6s over 3s plus 1. And the parameters of the model simply are 1.6 seconds for the time delay. The process gain is 3, and the process time constant is 3 seconds. Okay, so that's our FOPDT model. Now, how to develop the PI controller? The PI controller is from the design tables. We simply go to the tables that were given for the FOPDT model. Okay, so from our IMC correlations, Kc is given by okay, so from IMC tables for a PID controller. Okay, Kc was given by 1 over Kp times tau p over theta p. If you take a look at your notes, this was one of the coefficients. Let's calculate that. 1 over 3 over 1.6 plus what is our tau? Oh, sorry about that. Now we need something here, right? Tau c. But what is tau c? Okay, remember tau c is a design parameter which specifies what's our desired final response. Okay, so select a desired response as a desired overall time constant. Okay, here in the tables we have for moderate performance, we had tau c selected as the maximum of tau p and 8 theta p. That is the maximum of the process time constant is actually 3, and 8 times theta p is given by 12.8. Okay, so that gives us 12.8 seconds as our overall desired time constant. Okay, so this thing becomes Kc becomes simply from putting in tau c over there, right? 1 over 3 over 1.6 plus 12.8, and that will give us 0.069 for the controller gain. Also, we need tau I, the integral time constant, from the tables that is given as being equal to the process time constant, and that is equal to 3 seconds. Okay?
Hocam bir tau c tam olarak tanımı ne oluyor tau c'nin?
Tau c is the desired overall time constant of the overall closed loop system. This is a design parameter. Okay, so you have some design formulas. Okay, they depend on two things. The first thing is the model of the plant, and the second thing is what do you want the overall behavior to be. Okay, So you specify this overall behavior as a time constant. So the overall system will behave as a first order response with tau c time constant. Okay? The smaller tau c, the faster the system. The larger the tau c, the slower the system. Okay? So this is your design, is the design parameter. Obviously, the model parameters are coming from a model of the plant. Okay? So on top of the model of the plant, you specify what do you want the overall behavior to be. Remember the transfer function of the controller, right? We found Kc and tau I. What was the transfer function? It was Kc 1 plus 1 over tau I times 1 over S. Okay? So let me also put the block diagram of this of the overall system. Okay, in fact, a detailed block diagram. So we have the reference signal R of t here, right? We need to have the controller here. The controller feeds the plant, GP of S or G of S. I don't remember whether we said G of S or GP of S. Okay, but this is the plant. So there is the feedback. And let me put the controller here. So we have 1 on one branch. And we have also 1 over 3s on the other branch, which is this term over here, right? These are summed up. And they are also subjected to the final gain, right? So we have 0.069 as the controller gain, and that feeds our plant. Okay? All right. Now, do you guys have any questions? So when somebody tells you, give me the detailed block diagram of the controller, this is the most amount of detail that you can have. Okay, basically all the coefficients and all the terms are different blocks here, which shows the overall. But if we want to talk about the controller, this is the controller, right? This whole thing. If this was kind of collected as a single block, this is our GC of S. Okay? Any questions so far?
Hocam ben bir tane daha sorabilirim.
Sure, go ahead. Who's speaking?
Ben hocam.
Siz Ege. Okay.
Pardon.
Şeyi görmüyorum, o yüzden şu anda burada sadece benim görüntüm var. Yes.
Şey diyecektim de, eğer mesela sistemin kendi önceden de delay'i olsaydı, biz bu approximation'ı yapmadan, sonra approximation yapıp o iki delay'i topladıktan sonra mı ana delay'i bulacaktık, yoksa o ilk delay'i katmıyor muyuz?
Bu sorunun cevabını bence siz verebilirsiniz bana. Sizce?
Bence katacağız gibi düşünmüştüm ama.
Yani doğru düşünmüşsünüz. Yani sonuçta sistemde bir delay varsa, siz de bir approximation sonucunda ekstra bir delay ortaya koyuyorsanız, tabii ki sistemin overall davranışı bu iki delay'in combination ile ortaya çıkacak. Yani sistemde var olan bir delay'i ignore edemezsiniz ki. Yani sonuçta o hani onun da bir etkisi tabii ki mutlaka var.
Anladım hocam. Şeyde kafamı karıştırmıştı da, bu first order'a approximate ederken acaba hani o ikisinde de delay olacağı için hem ana sistemde hem şeyde.
Remember what we have said. Any delay, the delay can be the delays may be due to different physical phenomenon and may be at different locations in the open loop path, but all the delays on the open loop path can actually be combined into a single delay mathematically. Because when you calculate the open loop transfer function, you multiply all the transfer functions of the individual blocks along the open loop path. And once you multiply exponential functions, obviously the exponents will be added together. And that means the delays at the exponents will be added together and they will become a single exponential function. So mathematically speaking, it doesn't matter where the delay is over the open loop path. You just need to consolidate all of them into a single exponential function. Okay? Any other questions?
Ben de bir şey sorabilir miyim?
Who's speaking?
Mustafa hocam.
Okay, go ahead.
Şimdi hocam biz bunu bu sistemdeki polları bir time delay olarak atıyoruz ya. Bu aslında transient behavior olan fikrimizi daha azaltsa da settling time ve settling time, rise time ve MP gibi değerleri daha iyi bir bulabilmemizi mi sağlıyor? Transient kısmında çünkü aslında o delay değil de başka bir şekilde etki edecek. Yani biz delay olarak oluyoruz.
Şimdi şöyle düşünelim. Şuraya bir örnek çizeyim size. Şimdi diyelim ki bir sistemimiz var. Sistemimiz normalde bir higher order bir davranış gösteriyor. Yani şuralarda bir şeyler yapıyor. Sonra böyle bir davranış gösteriyor. Yani şurada olan olaylar non-dominant behavior. Şuralarda olanlar ise dominant behavior. Neden? Çünkü daha yavaş olan exponential'lar sonuçta bu taraflarda, sağ tarafta ne olduğunu belirleyecek. Çok hızlı die out eden exponential'lar ise şu başlangıçtaki zamanda olup bitecekler. Doğru mu? Şimdi burada olup biten olayları siz tümüyle non-dominant pole'lar olarak çöpe atarsanız o zaman aslında şöyle bir şey yapmış gibi oluyorsunuz. Hani bunları attığınız zaman aslında siz şöyle bir without non-dominant poles. Eğer bu pole'ları tamamen çöpe atarsanız aslında şu mavi eğriyi elde etmiş oluyorsunuz. Şimdi bakarsanız yeterince ileri zamanlarda mavi eğri ile kırmızı eğri birbirine yaklaşacak gerçekten de. Dolayısıyla yeterince uzak zamanlarda aslında ikisi de birbirine yakın. Ama mavi eğri yerine şöyle bir şey kullansaydık, mesela sarı eğriyi kullansaydık, yani şurada bir time delay ve sonrasında bir first order response kullansaydık, aynen dediğiniz gibi mesela ben bir rise time tanımlasaydım, yani şuralardaki zamanlarda mesela ti gibi bir zamanda baksaydım, bu ikisi arasında aslında bir approximation farkı oluşacaktı. Dolayısıyla rise time gibi mesela bir hızla ilgili bir performans measure'ına baktığınızda aslında non-dominant pole'ları bir time delay ile modelleyip arkasından non-dominant dominant pole'ları koymak en azından küçük zamanlarda bize daha iyi bir approximation vermiş oluyor. Cevap oldu mu?
Evet hocam, çok teşekkür ederim.
Okay. Alright. So is there any other questions? So I guess that's the time for our class exercise. Okay. So let's cover that, and then after that I will continue with the direct synthesis method, okay, which will lead to these design formulas for the PID controller. Okay. Evet arkadaşlar, kaydımızı donduralım.